Hello everyone, my name is Shen. It's my great honor to present our paper at WCB 2024. Our paper is titled TPSeNCE towards artifact-free realistic ring generation for deraining and object detection in ring. And this project is advised by Dr. Srinivasa. Here's outline for today's presentation. Now let's start with challenging for object detection, which is very crucial for autonomous driving. On the first row, we show that the raindrop on the windshield will significantly impairs the visibility of the object outside the window. On the second row, we see that if there's standing rainwater on the road surface, the object detection algorithm will be very confused about the object outside. One naive way to utilize ring generation algorithm to generate rings. And later we can utilize these generated ring images to fine-tune the object detection algorithm. However, as shown in this figure, current ring generation algorithms tend to generate images with lots of artifacts and distortions with unrealistic amount of rings. We attribute the artifacts and distortions due to non-proper constraint, and we attribute unrealistic amount of rings due to non-effective strategy to control the ring generation process. To address the issues mentioned above, we propose our TPSeNCE, which has the brief workflow shown in this figure. So in the upper half of this figure, we have the clear image, we have generated image, and ring image forming a triangular relationship. Ideally, if we compress that triangular towards the line segment, then we'll have maximum feature overlap between the clear generated and ring image, leaving no room for artifacts or distortions. On the lower half, we take the clear image and generated image to go through optimal transport to get the pixel level similarity. Meanwhile, we take the clear and ring image go through semantic segmentation to get the semantic information similarity MPA. Now, using the MPA and similarity, we can compute the construct learning force or weight to regularize the ring generation process, so we can automatically control the amount of rings we want to generate. And here's a more detailed workflow for the proposed methods. So proposed method is based on generator adversary network or GAN. And first, we utilize the generator to generate ring facts upon the clear image. After that, the clear image, the generated image, and the ring image together will go through the discriminator to compute the TPS loss and also the GAN loss. On the other hand, we utilize a pre-trained semantic segmentation model to get the segmentation map for clear and raining. Now, together with the clear and generated image, we go through the encoder to get the sense loss. Now finish the overall workflow for the proposed methods, let's move on to more technical details, starting with the motivation of the first component, TPS. In this figure, we show the TSNE visualization, or TPS. Basically, we show the clear image, the real ring image, and the generated image feature distribution together. Here we notice that the good generated image has lots of feature overlap for clear and real raining, leaving little room for artifacts or distortions. Meanwhile, the bad generated images has very little feature overlap for clear or real raining, and the rest has lots of artifacts and distortions. So based on the motivation above, we want to design a loss function that suppresses the generated image towards the real raining and the clear image to maximize the feature overlap and also to minimize artifacts and distortions at the same time. Based on triangular inequality theorem, we design this triangular probability similarity loss or TPS loss. Now, intuitively, TPS loss kind of take the summation of two sides of triangle and divided by the other side of triangle. If TPS loss is equal to 0, then we are basically compress that triangular to a line segment. Now, finish the TPS loss, let's move on to the second contribution, which is called sense. Now, our idea in this regeneration is to generate some ring effects upon the clear image. But due to the instability of GAN training, usually we're ending at the position of Z1 where we have insufficient ring. Or sometimes we end at Z3 where we have excessive amount of rings. As we can see here, Z1 or Z3 is not as realistic as Z2. So in Z1 here, I want to minimize our sense loss. That way, the GAN loss will be the sense loss between Z1 to Z2. So more ring and more realistic. On the other hand, if we write as Z3, want to maximize our sense loss, the sense loss will be the GAN loss and bring Z3 back to Z2. So again, here we have less ring, but meanwhile more realistic. And here the formula breakdown for the sense loss. So given the clear image X, the real ring image Y, and generated image Z, we take the negative summation or log of the positive patches divided by the positive patches plus all the negative patches. Here we're using adaptive weight Wij, which equals to softmax function, this Fij divided by this hyperparameter beta, where this Fij is equal to intuitively the agreement and disagreement between the semantic information MPaXY and the pixel level information Xi multiply Dj. Okay, now finish the proposed modules. Let's move to the experimental results, starting with the quantitative comparison on clear deraining or regeneration. So here we notice that our methods leads to the best performances for regeneration of both BDD 100K and init in terms of both user study scores, including content style, and distance-related matrices, including KID and FID. We also show the opposite ways draining to clear or deraining. So here we train the model SAPNet upon the generated rain images from different methods, including ours. Then we tested the trained SAPNet model on the BDD 100K rain images. We noticed that our generated rain images lead to the best deraining performances, which is reflected by user study scores, quality and performances, and also non-reference image quality scores, MUSQ, and DBCAN. Finally, we show the quantitative comparison for object detection rings, where similarly we first fine-tune the ULOB3 object detection algorithm upon the generated rain image from different methods, and then test it on the rain images to get the MAP score. And here our methods lead to the best object detection performances, regardless of IO threshold or object sizes. Now finish the quantitative comparison, let's look at some qualitative results, starting with this clear deraining or regeneration, where our methods can generate quite realistic rain images with little artifacts or distortions. And for raining to clear or deraining, our methods lead to the best deraining performances, which reflected by the blue sky and the dry road surface. And also for object detection rings, our methods lead to the best object detection, both in terms of classification and also localization. We also extend our method to other time of day and value vector. For example, here we show day to night translation, where our method generates quite realistic night scenes, where others like CAD, QSDN still have some daytime features in these night images. And also we try clear to snowy, where our methods can generate quite realistic snowy images. And on the other hand, CAD cannot generate enough snow on the surface, whereas MONC generates this ice cream texture like a snow, which is not realistic. So in conclusion, we propose TPSeNCE and non-paired image-to-image translation framework, and we show rain generation benefit deraining and object detection in real raining conditions. Our method can be easily generated to snowy and night scenes with great performances. So for the future works, we want to explore extremely heavy rain, which might involve drawing pre-processing and fine-tuning. We also want to incorporate physical-based methods for dealing with strong light sources, and finally try our proposed strategies on the recently popular diffusion models. And here the first page for references, and here the second page for references. Finally, we would like to appreciate General Motors ECO for their funding and support for this project. So if you are interested, please scan the QR code to access our GitHub webpage for more details. Thank you so much.